We're going to speak about what Art Ludwig has coined monolithic reinforced Adobe. Art Ludwig is an ecological systems designer with 35 years full-time experience in water, wastewater systems, energy, shelter, and human-powered transport. His specialty is complex, integrated systems of systems. Art has studied and worked in 27 different countries, attaining fluency in 5 languages. He has consulted for the states of New York, California, and New Mexico on water reuse policy and building codes, and given dozens of lectures and workshops. He has developed numerous innovations which have been adopted worldwide, incorporated in building codes, all of which he has published into the public domain. Art has authored numerous articles, as well as the books Water Storage, Principles of Ecological Design, and Create an Oasis with Greywater. The past several years, Art has dedicated approximately 1,000 hours a year to public interest research and sustainability policy activism. He is spearheading the seismic testing of reinforced monolithic Adobe in collaboration with Cal Poly Civil Engineering and Quail Springs, and is a contributor to the recently submitted Monolithic Adobe Appendix to the International Code Council, the ICC. I'd like to welcome Art Ludwig to the stage.
Thanks, Ray, and thanks for y'all come out today. So I want to talk about the permitting for the climate-safe, firestorm, and earthquake-resistant earthen building, aka Fun with Codes. Now, I always like to start with gratitude. I appreciate you all taking the time to come out today. And I'd like to give out shout-outs to a few of the hundreds of collaborators that have had a hand in this effort. Doug Hensel was the fellow at the Department of Housing and Community Development who I worked together with to rewrite the California Greywater Code in 2009. Martin Hammer, who was just mentioned, he's the author of the straw bale and straw clay appendices to the building code, and he just submitted the Cobb appendix 2 weeks ago. Go, Martin. Cal Poly Slow, who's been helping a great deal with the structural testing. Verdant Engineering in Berkeley, which is probably the premier monolithic Adobe engineering firm in the Western Hemisphere, and has had a big hand in the code, as well as a project we're working on in Santa Barbara. Bill Kelly, the chief building official of Marin County. He's my codes guru, and we've also worked together at the state level on some code stuff. And then locally, Jim McDonald, Matt Wyatt, who's here with us today, Chris Stevens, and Kathy Long, who took the trouble to adopt the Limited Density Rural Dwelling Code, which is an alternate compliance path that allows more flexibility for owner-builders to innovate in remote areas of Ventura County. So the goal of my work is a high quality of life with a low ecological footprint. And the best way I've found to achieve this by far is with a process that I call optimal integrated design. And this consists of getting clear on your goals, assessing the context, all the relevant factors, assessing the issues, the resources, using those resources to address the issues, getting as quantitative as needed, doing testing if you need to, optimizing the connections, and then repeating and refining as needed. Sometimes you need to do about 2.5 tries to get it right. Some of the elements of the work that we're doing these days are structural testing, fire testing, code improvements. Working on a code compliance package is kind of an ultimate long-term goal for fire-resistant earthen accessory dwelling units and or tiny houses. So that's something that would help people on both sides of the permit counter to kind of get things through easily. This thing that's pictured here is a monolithic Adobe tiny house village that we're currently in the permitting process for in Santa Barbara. Downtown. It's in seismic zone E. It's the hardest seismic zone. It's also the hardest regulatory zone. And we're hoping if we can establish a precedent there, that'll make it easier for people in other places. And this is a video fly-through of the project. What's that? This is all of monolithic Adobe. We went really big on the integrated design here. It captures all the storm water, stores it in the soil to meet the irrigation need. There's very high water efficiency. We've got the water meter right there between the kitchen sink and the front door. Whole thing is non-combustible. It has built-in non-combustible furniture to reduce the fuel load. Gets far greater fire safety. And it's all the Adobe is steel mesh reinforced. This is a system that we've been working on with earthen builders in Santa Barbara and Ventura County. This double mesh system where the Adobe is completely encased, we feel is particularly promising. Look forward to the test results on this. So anyway, that gives you a little bit of a feel for that project. In optimal integrated design, you design for all the relevant factors at once. And this is a partial list of the factors we're considering in this design. Global safety, including the non-combustible construction, which is also non-toxic and non-off-gassing. Low climate impact, I'll talk some more about just how significant that is. Earthquake reinforced, low car use, high biking and walking. Also global affordability, which has a bunch of components to it as well. And ultra-high efficiency water use, as well as alternate supply and reuse. And my specialty is kind of optimizing the connections between different systems. And one nice thing with this is if you have ultra-high efficiency, the municipal code was actually altered in Santa Barbara. Ordinarily, a project like this would require 6 water meters. And because of the ultra-high water efficiency fixtures, they're allowing us to use our existing single 5/8" meter. And we're expecting that all 5 units together will use half of the water of an average unit in Santa Barbara. And because of having the smaller water supply, if in the highly unlikely event these structures burn down, there are much smaller leaks and water loss to the municipal water system, which means more water available to fight an urban firestorm, where a whole bunch of the city's being attacked at once by fire. Secure government revenue. This is sort of one I hadn't really thought about. The last time I gave a version of this talk, it was a month or so ago in Lake County, and the county government kind of had its revenue knocked out from underneath it by losing a significant fraction of the housing stock in the county. So right when they needed it most, they were defunded. So if you have a housing stock that's less likely to burn down, your property tax revenue is more secure. I was invited by Bill Kelly to give a talk on this building system and alternate materials and methods at the annual conference of county building officials in 2013, and I'd like to share a few slides from that talk. Some of these statistics may seem kind of amazing. This is an analysis I did. I just wanted to preface it by saying that this fellow Richard Jackson vetted this analysis. He's one of possibly the world authority on hazards attributable to the built environment. He's the chair of environmental health sciences at UCLA. He said it was perhaps the best global analysis he'd seen of these issues, and all the assumptions and calculations are on our website at that URL below. So this is a graph that shows changes in hazards attributable to the built environment over time. And this is where you start to not see parts of it. Starting in 1800, going in time, there's a vertical line that's almost invisible, it looks like on the screen right here for the present day, and going to about 2050. On the vertical axis, which I unfortunately see is cut off, it's deaths per million per year. So that's 20, 40, 60, 80, 100. And just for scale, right now car crashes are killing about 106 Americans per million per year. And this trend line here shows deaths, mortality from earthquake and structural collapse per million per year. That spike is the San Francisco earthquake. And then you can see that it's trending down over time. These are structure fire deaths, and you can see that this is trending down really strongly over time. And just in the last 40 years, structure fire deaths have been cut by half. So this is a tremendous victory for building codes. And this crazy line is deaths from waterborne disease. And this is just plummeted. So this is really the success of modern building health and safety codes in one slide. And there's a lot here to be justifiably proud of on the part of conventional building science, has really done a remarkable job here. Oh, one of the things that's interesting about this, and I'm going to dive into it more later, is just the proportionality between these different threats. And there's a principle to apply regulatory resources in proportion to the hazard. So here this line is showing that 330 times as many people die in structure fires as die from earthquakes, even though we sort of think of them as like being kind of on parity. Now we're going to turn to kind of a different story, which is changes in hazards, emerging hazards attributable to the built environment. So this is a line for heart disease, modern built environment, and this is more of a planning issue than a building code issue, but it's more difficult to get around under your own power on foot or bike, and that has contributed to a small portion of the giant increase in heart disease, mortality attributable to heart disease. And then more directly from buildings, there's an uptick in cancer attributable to cumulative toxin exposure in buildings. There's a huge long laundry list of toxins in buildings. That fellow Richard Jackson did a bunch of tests when he was head of a large division of the CDC, finding these, that these materials weren't just in the structures, they were also in the tissue of people living in them. And that's contributed to some of the giant increase in cancer. Currently, I think it's 1 in 3 and 1 in 2 women and 1 in 2 men that will develop cancer. And a portion of that's from the built environment. And then this crazy, scary line is mortality attributable to climate breakdown. And these are all hazards that are almost entirely off of the radar of modern building codes and are growing very rapidly. It's also worth noting that each one of these by itself is bigger than all 3 of the top hazards of historical concern combined. In this slide, I wanted to dive in a little bit more to this proportionality between different threats. So for each one person that dies from earthquake, we've got hundreds that die in structure fires. And in the building code, these 2 hazards are treated exactly the same. You have to do all the measures for structure fires, and you have to do all the measures for earthquake. If you can save 100 people from dying in structure fires for half a person more dying in structural collapse, you can't do that kind of horse trading in the regular building code. There's no place, unfortunately, for common sense in the code. And one thing which I would like to point out is don't berate your code official for this. They didn't write the codes, and once you get to the counter, there's literally nothing that either of you can do about it. You have to do all of the, if you want to change the rules of the game, that has to happen in Sacramento or at the County Board of Supervisors before you get to the permit counter. So once you get to the permit counter, the only discussion you can have is how to check the boxes that need to be checked. And earthquake needs to be checked, and fire needs to be checked. So this is a case where the only remedy really is to go back and take another look at the rules. So suppose you're proposing a structure that's twice as dangerous for earthquake, but a third as dangerous for structure fires. Like we were saying, you have to change the rules in order to be able to successfully make a case that, hey, this is actually a safer structure overall. So that's what it looks like just looking at those hazards. And then the picture gets quite remarkable when we look at these emerging hazards. And I just want to draw your attention to the fact that the scale has jumped quite a bit here. This is 300 deaths here. This is 3,000 deaths there. And this scale goes up to 8,000. So 266 deaths from structure fires are now this tiny little box there. And then there's the cancer from cumulative toxin exposure from structures. And then there's climate disruption. 4,400 deaths per earthquake death. And you're probably hearing this, I think it's safe to say you're hearing this for the first time. And this is something that's just, we have an older paradigm for addressing hazards from the built environment that just really has not digested how this is changing. And to put this into perspective, let's say that hazards from climate disruption are increasing 10% a year, which I think is probably fairly accurate enough. That means today's increase in climate hazard is bigger than the entire hazard from earthquake. Just today's increase in climate hazard. So this is something we really need to address. And this is something that we're looking forward to collaborating with policymakers and regulators to address and get this total hazard number way down. It's a great time to refocus safety efforts. We just went over this. Oh yeah, I didn't know about this either. Heat is already the #1 weather-related mortality factor in the United States. It's more than every other factor combined. Hurricanes, flooding, firestorms. Heat is killing more people. When have you heard about heat? These days, community after community is faced with the question how to rebuild after an urban firestorm. And the answer is pretty much the same as what just burned. And that's framing and modern materials, which could be fairly characterized as a mixture of kindling and toxic waste. And even if you skin this thing with stucco and put dual pane windows in it, that's still a lot of fuel. The Wildland Interface Building Standard shielding is partially effective, but many structures will burn anyway because of the intensifying conditions. So these red circles are building losses in the Thomas fire that had the high fire resistive, these higher fire resistive factors mentioned there. So with this, now that we're facing loss of 10,000 homes at a time, might there be a safer way to rebuild? This is Taos Pueblo again, 1,000-year-old structure, and the oven is made of the same material as the house, so highly fire resistive. Monolithic Adobe is non-combustible, non-toxic, non-off-gassing, heat-absorbing, insulating, and structurally sound and load-bearing even under extreme heat. We've got the seismic testing in progress, getting the engineering constants we need for seismic zones B through E. We're looking to do fire testing. There's been some testing already done. Every large-scale standardized test that's been done has passed with ratings from between 2 and 4 hours. And that means no integrity failure, no flame passage, no excessive heat rise on the cool face, load bearing even under heat. The test that went to 4 hours, they thought that it would actually go to 6 or 7 hours before the cool face breached the insulation standard. It would be great to do official testing for monolithic Adobe. This video is of a test of straw bale, which was part of getting that in the uniform code. I'd like to race through some fire details for the new climate, point out some fire mistakes in this picture. We've got what I call decorative fuses that this is my dad's house. These caught embers in the Jesucita fire and then burned through these vigas into the little attic cavity between the ceiling and the roof. And the firefighters that just happened to be sheltering in his house had to chop through the ceiling to get at it to put it out. So if you can, just build without cavities. There's the wooden rail and then the wooden deck. So some details, windows. I can't think of any, right now they're required to be dual glazed, but only one of them's tempered. Just make them both tempered. If you're building a cob house, you can get free dumpster tempered glass out of the dumpster behind any glass shop because they can't recut it. And often it's really thick and nice, way more than anything you could buy. And when you can cast these directly into the cob walls, and the cob itself acts like the silica gel and pulls the moisture out from between the panes. Fire mistakes in this picture. Well, we've got oil lamps and incense and some photographs exposed to radiant heat through the windows. The windows are single glazed, untempered, that's supposed to say, and in wooden frames. So instead, if you're building in a high fire area, just slope the windowsills, make it impossible for stuff to accumulate there. This is a trick that I learned from doing fire drills. This is something I'd recommend. Do fire drills and then make permanent changes that eliminate this sort of step of like clearing stuff away from the windowsills. Raking mulch away from buildings is also tedious. You could make a masonry skirt that slopes to automatically continuously shed mulch away from buildings. You can leave windowsills and trim out completely like this window, or use fire resistive low conductance windowsills like this granite sill. I don't know if shiny surfaces reflect radiant heat as well as they do visible light, but I'm going with colored aluminum frame windows rather than black, and going with shiny hardware as well these days. These are some fire shutters that we made. These don't comply with the new art fire code. This is about 10-year-old art fire code. The new ones that I want would roll down automatically after heat fusible link breaks. Fire-resistant blinds is an interesting thing to look at. This structure survived when everything else burned, possibly because of these light-colored aluminum blinds. If you're retrofitting a home, a tiny bit of clay paint adds an amazing amount of fire resistance over wood. And here we covered wood trim with clay, and we packed clay underneath very effectively ember-catching wooden threshold. Doors. Metal doors, no good, as it turns out. Heat goes right through it and bakes you. And there's an account from Australia where their $1,000 fire door heated up so much that it warped and wouldn't even shut. So that was kind of alarming. So what we did is we covered it with earth. So these may be the only 2 Adobe doors in existence, but I'm feeling, very secure about the Adobe door on my office. Roofs. There's a sneaky building destroying fire mistake in this picture. Not so much the curtains, it's the asphalt underneath the tile. So the gutter catches leaves, and then that gets the soft underbelly of that asphalt roll roofing, and it's actually about as flammable as this roof. And this is a photo of a house that Yanto and Evans and I checked out after the T-fire, brick with a tile roof, and the thing was a total loss from that mechanism. This is a test I did. I don't trust fire ratings anymore after doing this. This is a Class A shingle, and I told Yanto, it must have something in it that keeps it from burning. He's like, it's tar, Art. He's like, no, it's Class A. I must be quadruple protected with all these layers. He's like, let's try it. So, yeah, there goes the flame, and then you can see the flaming, burning drops coming off of the back of it. So no more trusting of fire ratings. If you want to know if it's any good, heat it up and see if it burns and if it puts off toxic gases. We use metal roofing with metal framing and fiberglass EcoBat that has non-toxic, non-flammable binder, screen on gutters, or a ferrocement roof, which is entirely non-combustible. The eaves are non-combustible. You've got the metal rafter tails with expanded metal lath and either earth or cement stucco. What about these crazy plastic things over the solar tubes? How can that be legal? We took ours off and put an oven-safe, heat-resistant Pyrex bowl over it. Hopefully that'll work. You can get tempered glass and you can get wired glass, but you can't get wired tempered glass. But you can make it yourself by sandwiching wire between 2 layers of dumpster tempered glass, like we did here in these photos. Decks and rails, no more redwood decks, sorry. Once it burns off, rebuild it with something non-flammable. I was hoping that these turbine ventilators would not allow embers in, just like they don't allow rain in, and I got a first-hand account from the Woolsey fire saying that was the case, that embers did not come through these vents even though they were spinning around vigorously. You can put metal blast gates on the inside to seal it off as well. Bunch of other little details, metal vents with screens on them, screens for leaves and rats at every crevice in the metal roof. You got to have extreme care with utility penetrations. And that's it. If you want to help out with this research, there's a page on the Quail Springs website where they're taking donations. Thanks.